screen, stuff like that. Okay, I was going to do a couple more curve sketches, but I wanted to get started on section 4.7. Okay, so, and I wanted to make sure I finished by next Tuesday. There actually isn't as much time as you might think. So I'm trying to zoom ahead somewhat and do up to 4.7. So my goal is to finish everything by next Tuesday the 10th, because Wednesday is a holiday. Then Thursday will be Q&A session, and then the test is Friday, right? Okay, so I'll do some more curve sketches. Then I'll stop doing curve sketches so I can get started on 4.7. Now I think I put 4.6, but there is no 4.6, right? We're not doing 4.6. 4.6, the topic is graphing with calculus and calculators. Well, I'm not requiring to have a graphing calculator, so that's why we're skipping 4.6. Even though it says 4.6 on the schedule, we're not doing 4.6 at all. So it's almost like that's off the table, so to speak. Okay, so we're going to go from 4.5 to 4.7. Now I was going to do 2 more curve sketches today, and then depending on how long it takes, I was going to get started with 4.7. And what's 4.7? 4.7 is applied max-min problems. They're practical situations where you might want to maximize or minimize some quantity. Okay, so you see applied max-min problems, so to speak. Okay, but let me go back to again. So the homework is only, quote unquote, every other odd. So that's 1, 5, 9, 13, and so on. I did some, I'll do some more, but they're long, there's no question about it. The problems are somewhat long for those. Okay, so let me show you question number 5. Y equals x times x minus 4 cubed. Okay. Now, you could multiply that all out. I don't feel like doing it. You probably don't feel like doing it either. So let me just take it as is. All right, so take 2 derivatives. Product rule, right? First times derivative of second, x times 3x minus 4 squared. By the chain rule, it's times the derivative of the inside, but that's just 1, so don't worry about it. Plus second function times the derivative of the first, which is just 1. So I have that. Okay. A little bit of cleanup is nice, especially when you're setting it equal to 0, but also for the second derivative's sake. So I can factor out an x minus 4 squared, right? That has x minus 4 squared. That has x minus 4 cubed, which means I can take out x minus 4 squared. If I take out x minus 4 squared, this will have 3x. This will have another x minus 4. Right, so grand total, 4x minus 4, x minus 4 squared. So if I have to set this equal to 0, this is pretty easy to set equal to 0. Okay, but it's also better to have this for the second derivative. All right, so y double prime, again, it's a product rule. First times the derivative of the second. Derivative of the second is 2 times x minus 4 times the derivative of the inside, but again, that's 1. Plus second function, x minus 4 squared, times the derivative of the first, the derivative of this is 4. And again, it's best to have it factored. So there's a common factor of x minus 4, right? So take out an x minus 4. This will have 2 times x minus 4. This will have 4 times another x minus 4. If I take out an x minus 4, there's still another left. All right, clean this up. That's 8x minus 8 plus 4x minus 16 for a grand total of x minus 4, 12x minus 24. Factor out to 12, x minus 4, x minus 2. All right, so I have the first derivative and the second derivative completely factored, so that's going to help me when I graph this thing. All right, so we're supposed to consider all the things like domain, intercept, symmetry, asymptotes from the direction, right? So all these problems have from that super long list. Right, so on page 315, consider A, domain, B, intercepts, C, symmetry. Then on page 316 here, 316, the asymptotes, horizontal and vertical asymptotes, intervals of increase and decrease, local max and min, concavity, points of reflection, sketch the curve. Okay, so this is just about everything you can do with a graph, right? The whole works, as it were. All right. All right. This is a polynomial, so the domain is all real numbers. Okay. No forbidden values. Any real number will work. Any real number, I can subtract 4, I can cube it, I can multiply it by itself. Where do you have to watch out that you don't have all real numbers? Well, if you're dividing by something, you can't divide by 0. Square roots, right? You can't take the square root of a negative. Trig sometimes causes some issue. Natural log, you can only take the element of positive quantities and stuff like that. Okay, but for this one, domain is all real numbers. Intercepts. Okay, when I plug in 0, I get 0. And if y is 0, then x is 0 or x is 4. So the intercepts are 0, 0, and 4, 0. Okay, so it's going to touch the x and y axes only at 0, 0, and 4, 0. This is the entire graph, but right now we got that, and the graph will touch the x and y axes nowhere else. Symmetry. To test for symmetry, you replace x by negative x. Back here, put negative x here, put negative x here. Looks like that. Okay. And if you get something equivalent to the original, then we have an even function, and we have symmetry with respect to the x-axis. Is that the same as that? The answer is no. Algebraically, they're not the same. We would have an odd function if this is the opposite of this. In other words, is it equal to the negative of that whole thing? Algebraically, that's also a no. So there's no symmetry. And you can kind of see from the final answer. Asymptotes, there are no asymptotes. See, how can I find asymptotes? Well, there are no vertical asymptotes because the function's always defined. Okay, so let's say if you would divide by x minus 2 or something like that, then x equals 2 might be a vertical asymptote. The next problem I'll show you will involve something like that, but this one doesn't have that. And there's no horizontal asymptote. When x goes to infinity, y goes to infinity. When x goes to negative infinity, if I plug in a negative big number, negative 1,000,000 times negative big number cubed, you get a positive big number again. Okay, so that tells me we have no asymptote. All right, so I'll go straight to our derivative test. Okay, so set f prime equal to 0. Set that equal to 0, I get x equals 1 and x equals 4. Okay, plug in 1, I get negative 27. Plug in 1. 1 times 1 minus 4 is negative 3. Negative 3 cubed is negative 27. So 1 comma negative 27. And 4, 0, we already got that, right? 4 comma 0. Where'd it go? Right here. Okay, then I do my sign chart. Put down 1 and 4. Here's f prime. If I plug in 1, I get 0. If I plug in 4, I get 0. Everywhere else, I do not get 0. That means it's either going to be positive or negative. Okay. So pick something in each region. Something over here, here, and here. So what's over here? 0. What's in here? 2. What's over here? 5. Okay. And my sign chart's going to be fairly easy, actually, because I notice I have x minus 4 squared. It's blah, blah, blah squared, which means automatically positive, 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 right? So the sign is completely determined by this, 4x minus 4. You plug in 0, 4 times 0 minus 4, negative. Negative times positive, negative. Plug in 2, 4 times 2 minus 4, positive. Positive times positive, positive. And something over here, 5. 4 times 5 minus 4, positive. Positive times that, positive, positive. Negative, positive, positive. So negative first derivative, decreasing. Slope negative. Function decreasing. Positive first derivative, increasing, increasing. Okay. That's what I have. So what does that mean about x equals 1? If your roller coaster goes down, then it goes up, I have a minimum. How about at x equals 4? It goes up, and then it still goes up. That means you don't have either a maximum or minimum. Okay, so intervals of increase and decrease. So f is decreasing from negative infinity to 1. F is increasing from 1 to 4, union 4 to infinity. Again, very technically, you can't just say 1 to infinity, because right for a split second at x equals 4, the slope is 0. So it levels out to a slope of 0, but then it goes back up after that. Okay. So it looks like I have a minimum at 1 comma negative 27, but there's no maximum. Right, first derivative analysis is done. Second derivative, I pretty much do the same thing. Set f double prime equal to 0. So double prime was here. Set that equal to 0. That gives me x equals 4 and x equals 2. Okay, plug in 2. Let's see, negative 16. 2 times 2 minus 4 is negative 2. Negative 2 cubed is negative 8. 2 times negative 8 is negative 16. And we already got 4, 0. So 4, 0 is showing up quite a bit. Now I do my second derivative analysis. Y double prime, 12 times x minus 4, x minus 2. Okay, so this time I lay down 2 and 4. Why do I put down 2 and 4? The second derivative was equal to 0. So everywhere else, the second derivative is not 0. That means it's either positive or negative. So just determine the sign. Pick something here, here, and here. Okay, so what's over here? 0. In here, 3. Here, 5. Plug in. 12 is already positive. So that plus, plus, plus is for the 12, which is already positive. Okay, 0. 0 minus 4, negative. 0 minus 2, negative. 2 negatives, positive. 3, that's already positive. 12 is positive. 3 minus 4, negative. 3 minus 2, positive. Multiply them all together, negative, negative. And 5. 12 is positive. 5 minus 4, positive. 5 minus 2, positive. Multiply them all together, positive. This is the second derivative. Second derivative positive, concave up. Second derivative negative, concave down. You can put all this on your cheat sheet if you wish. So intervals of concavity are these right here. So the function concave up from negative infinity to 2, union 4 to infinity, and the function's concave down only between 2 and 4. Change in concavity, yes, inflection point. Change in concavity, yes, inflection point. 2 inflection points, 2, negative 16, and 4, 0. And I'm ready for the graph. Goes through the origin, touches 4, 0, minimum, inflection point, inflection point. Okay, let's look at increasing, decreasing. Goes down, up to 1, then from 1 to 4, increasing, and 4 to infinity, increasing. Concave up from negative infinity to 2, so U-shape. 2 to 4, upside down U-shape. And then 4 to infinity, back to being U-shaped. So there's the whole graph. So you can see these curve sketches are quite involved. There's a lot of stuff going on with these problems. Okay. Okay, that's number 5. The other one I was going to show you was 13, which has a lot to it also. So 13, y equals x over x squared minus 4. Okay. It's a rational function, so it's a lot more tricky, unfortunately. Okay, x over x squared minus 4, which factors into x plus 2, x minus 2. Okay, domain. Well, all real numbers minus the set consisting of -2 and 2. You can't plug in -2. You can't plug in 2 because you'll get a 0 on the bottom. But everything else is okay. So whatever the graph looks like, you can't cross -2 or 2. Intercepts. Well, 0, 0. That's about it. Right? Plug in 0, you get 0. If you set y equal to 0, that means numerator 0. So 0, 0. Okay, symmetry. F of -x. Put -x here and here. You get -x over -x squared minus 4. But -x squared is the same as x squared minus 4. Okay. This is the opposite of the original, right? -x over x squared minus 4 is the negative of this. Okay. So that means we'll have an odd function, which means symmetry with respect to the origin. This graph will have origin symmetry. Asymptotes. Okay. Well, when x approaches either infinity or negative infinity, okay, well, you can kind of tell, we did this before, x squared is going to beat x, so the ratio is 0. Or now that we know we have L'Hopital's root, right, this is infinity over infinity, you can take the derivative of the top, 1, derivative of the bottom is 2x, and now when x approaches either plus or minus infinity, you get 0. So I have a horizontal asymptote at y equals 0. And a vertical asymptote at x equals plus or minus 2. Okay, so we're going to approach x equals -2 and x equals +2 as asymptotes. All right, now for the derivatives. A little bit clumsy. Quotient root. So y prime bottom times the derivative of the top, x squared minus 4 times the derivative of the top is just 1. So I don't even have to write it. Minus the top, x, times the derivative of the bottom, which is 2x, all over the square of the denominator. Okay, I think I mentioned this before. Don't cancel these out. You're not allowed to. You might say, oh, x squared minus 4, cancel x squared minus 4. Nope, can't do it with the minus. Instead, clean up the top. X squared minus 4 minus 2x squared, negative x squared minus 4 divided by x squared minus 4 squared. Okay, and that actually makes part of the problem very easy. Okay, this expression I claim is always less than 0 for all x that's not equal to plus or minus 2. Okay. We already know we can't plug in plus or minus 2, but I claim the top is always negative. Look at negative x squared minus 4. That's for sure negative, right? If you don't see that, let's take the progression. What do you know about x squared? Greater than or equal to 0, non-negative. Put a minus. Now it's non-positive. That means negative or 0. Subtract 4, for sure negative. Okay, top's negative. Look at the bottom. It's blah, blah, blah squared. Automatically positive, wherever it's defined. So the ratio is less than 0. So this function's always decreasing wherever it's defined. So f is decreasing from negative infinity to -2, union -2 to 2, union 2 to infinity. Another way of saying this is it's always decreasing except at -2 and +2, because right at -2 and +2, function's not even defined. Otherwise, the graph is always decreasing. That means f is increasing nowhere, and therefore we have no max or min. How can we have no max or min? If we have a max or min, what would the slope have to be? 0. But we already found out this derivative can never be 0. Okay, so we're done with the first derivative. That's nice. And now I just have to worry about the second derivative now, which is not very nice. All right, so here we go. Just get right to it. So y double prime bottom times the derivative of the top. negative 2x. Minus, pretend it's a minus, top, negative x squared minus 4, times the derivative of the bottom. Derivative of that is 2 times x squared minus 4 to the first power by the chain root times the derivative of the inside, which is 2x. All over the square of the denominator, x squared minus 4 squared is to the fourth power. Okay, now what did I do? This is a negative, 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 so I made them all pluses. Okay, so plus, plus, plus. Now I try to take out common factors. Okay, so they both have 2x, comes out in front. They both have an x squared minus 4, x squared minus 4 squared, x squared minus 4. Okay, so I take out a 2x, x squared minus 4 to the first power. Okay, so look at this up until the plus sign. Okay, so what's left behind is a negative 1 times another x squared minus 4. Okay, so 2x comes out, x squared minus 4 comes out, but there's a square, so there's still another x squared minus 4 and negative 1. Okay, how about everything from here on out? Okay, I took out that 2x, and I took out an x squared minus 4. So these are all gone. So what's left is a 2 and an x squared plus 4. These cancel to become x squared minus 4 cubed. This is x squared minus 4 to the first power. This is x squared minus 4 to the fourth power. So one of these cancel one of these. I now have x squared minus 4 cubed. Go up 2x. Okay. Combine this all together. 2x squared minus x squared. X squared. 2 times 4 is 8. Minus a minus 4, plus 4, 12. So this is what I have. 2x times x squared plus 12 all over x squared minus 4 cubed equals 0. Okay. Set it equal to 0. When is a fraction equal to 0? When the top is 0. This can't equal 0. X squared plus 12 is always positive, so just x equals 0. So my only critical number is x equals 0, although I do have to pass through undefined values, 2 and negative 2. So on my number line, I do have to put down 0, 2, and negative 2. Switch to the other side for that. Okay, so y double prime is 2x, x squared plus 12 over x squared minus 4 cubed. So I lay down 0, negative 2, and positive 2. Okay, so 0 and the undefined values. So pick something here, 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 and here. So negative 3, negative 1, 1, and 3. And something you'll notice. X squared plus 12 is always what sign? Positive. So plus, 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 plus. Okay. Negative 3. 2 times negative 3, negative. Negative 3 squared is 9. 9 minus 4 is 5. 5 cubed, positive. You can see we don't really care about the exact value. It's too much of a bear to find the exact value. We just need the sign. It's negative. Okay, negative 1. 2 times negative 1, negative. I already know that's positive. Negative 1 squared, 1. 1 minus 4 is negative 3. Negative 3 cubed, negative. 2 negatives, positive. Positive 1. 2 times 1, positive. 1 squared is 1. 1 minus 4, negative 3 cubic, negative. So I have positive times positive divided by negative, negative. Finally, 3, everything's positive. 2 times 3 is positive. We already have that positive. 3 squared is 9. 9 minus 4 is 5. 5 cubed, positive. So positive. Second derivative, negative. Concave down. Second derivative, positive. Concave up. So here are the intervals of concavity. function is concave down from negative infinity to negative 2, union 0 to 2. F is concave up from negative 2 to 0, union 2 to infinity. Okay. That makes the origin 0, 0 an inflection point, change in concavity. Now, there is a change in concavity at negative 2 and positive 2, but we're not calling them inflection points because they're not even points, right? The function is not even defined at negative 2 and positive 2. Okay, so we can't say they're inflection points. We don't even have points there. So the inflection point is 0, 0. Okay, so trying to put all the pieces together. Here we go. Okay, asymptote, asymptote. When I go way out there and way out there, I approach y equals 0 because I have y equals 0 as a horizontal asymptote. Vertical asymptotes are plus or minus 2. Function's always decreasing, so goes towards 0, always decreasing, so goes toward negative 2. And over here, it's decreasing, touches here, concave up, switches to concave down, but still decreasing. This one's always decreasing, asymptote, asymptote, so it has to curve like so. So here's the entire graph. Okay. And you may notice it is an odd function. I have symmetry with respect to the origin. So a point here would reflect over to there. A point here would reflect over to there. A point here would reflect over to there, and so on. So here's the entire graph for the problem. Okay, so you can see there's a lot to it for these graphs. Okay, so that's as much as I wanted to show you for the graphs. Now, I might do more graphs as time goes by, but I want to get started with some of these applied max-min problems, of which I tiptoed around certain problems that I didn't want. So I couldn't just quickly say odds or evens. I had to look at every single problem and saw what I liked. So I liked some evens. I didn't like a lot of the odds, so you can see it's a weird assignment. Okay, but as usual, I'll end up doing a whole bunch, maybe the majority. We'll see how it goes. Okay, so these are sometimes called optimization problems. So 4.7. Optimization problems. Okay, page 230. They're basically max-min. Okay, so you might want to maximize an area, volume, minimize time, minimize cost, whatever. Okay, so we don't have to do an entire curve sketch. We would just do the portions of section 4.3 and 4.5, which gives us what we need. Okay, so we're normally not going to graph, although you might have to draw a picture for a lot of these, and you're trying to maximize something or minimize something. Okay. So here we go. Okay, problem 3. Find two positive numbers whose product is 100 and whose sum is a minimum. So you want to minimize the sum. Okay, so I'm going to show you what I have here. Two positive numbers. Okay, so I call them x and y. The product is 100. That means x times y is 100. And you want to minimize the quantity x plus y. Make that a minimum. Okay, so I'll lose the text now. Got it down to this. Okay, so at the moment I have two variables. I want to get it down to just a single variable. Okay, so to do that, normally we want to do problems involving x. So solve for the variable that is not x, which in this case is y. That's easy. Divide by x. Y equals 100 over x, right? So one more time, for these expressions, you'll quite often have two variables. Before I take derivatives and such, I want to just get it down to a single variable. So y equals 100 over x. Now I rewrite the thing that I'm trying to minimize, x plus y, as x plus 100 over x. And there it is. Okay. So what am I trying to do? I'm trying to minimize this. Minimize this, and we already know x is greater than 0, y is greater than 0. It said only have positive values. So there it is. I'm trying to minimize this quantity. So one more time, it said the product of two numbers is 100, positive numbers, okay? And you want to minimize the sum, minimize x plus y. So I've got it down to minimizing this, and we're only allowing positive values. Okay, so x plus 100, x to the minus 1. So f prime, 1 minus 100, x to the minus 2. F double prime, 200, x to the negative third, which I can rewrite as 200 over x cubed. Okay, and I notice this expression is always greater than 0 for all x greater than 0, which is all we care about, right? 200 over x cubed, for sure, positive. What does that mean? Concave up. If I have a concave up situation, if I set f prime equal to 0, I will have a minimum, right? Take a look at this picture. Here's a minimum. What do you notice? Concave up. For a maximum, it would go like that. That would be concave down. All right, so all I have to do is set f prime equal to 0, and I have it. I get my critical number. Okay, so my f prime was, where'd it go? 1 minus 100, x to the minus 2. 1 minus 100 over x squared equals 0. Multiply both sides by x squared to clear the fraction. X squared minus 100 equals 0. Add 100, take the square root. Normally, I would say x is plus or minus 10. They already told us that x and y are positive, so I want x equals 10. And y is 100 divided by x. So 100 divided by 10 is also 10. So my final answer is 10 and 10. So what are the two numbers? 10 and 10. All right, so the problem's actually finished, but I'll dig a little deeper. What is it saying? We know that 10 times 10 is 100. We know that. And what is 10 plus 10? 20. So we're saying any other combination of real numbers, positive real numbers, such that the product is 100, you can't get it any lower than 20. It must be higher than 20. Okay, example, 5 times 20 is 100. What's 5 plus 20? 25, bigger than 20. Okay. I could have 2 times 50. 2 times 50 is 100. What's 2 plus 50? 52. That's bigger than 25. All right. I could have 1 times 100. 100. But what's 1 plus 100? 101. Okay. And by the way, I only picked nice numbers. You could pick weird numbers, right? You can have irrational numbers, pi, fractions, decimals. Okay. Whatever combination you have, if you take the sum, it isn't going to be less than 20. Okay. The minimum value that we got was 20. Okay. All right, so that's number 3. Okay, and let's see, I think I'll show you number 7 next. Find the dimensions of a rectangle with perimeter 100 meters whose area is as large as possible. Okay, so the perimeter has to be 100, shaped like a rectangle, maximize the area. Okay. That is a practical problem because perimeter, that might be fencing, right? Let's say you have 100 meters of fencing. Okay, so you're limited to 100 feet, and how do I shape it so I get the maximum amount of area? Okay, so I draw myself a picture. The perimeter is 100. Area is x times y. And you're trying to maximize the area. So perimeter is 100. Think of fencing. Okay, x by y. Okay. And I'm trying to maximize x times y. All right, so if you look at this picture, P is 2x plus 2y. perimeter is 2L plus 2W. It's equal to 100. Okay. Solve for the variable that is not X in general. I mean, solve for Y. So subtract 2X, divide by 2. So Y equals 100 minus 2X over 2, which reduces to 50 minus X. So now that Y equals 50 minus X, I plug that back into here. See, before I take my derivatives, I only want a single variable. I don't want X and Y. I just want X. So I need to eliminate Y. Okay? And you can see I can eliminate Y by solving for Y here. Y equals blah, blah, blah. And then I plug that into here. Is that right? So now I have an area function that I'll call A of X. A of X is X times parentheses 50 minus X, which is 50X minus X squared. And I'm trying to maximize this with X greater than 0. Okay, and you might recognize that this is a parabola opening down. So if you have a parabola opening down, you will have a maximum. Right? And yes, there was a way to find a vertex without calculus. The formula was negative b over 2a. But now that we have techniques of calculus, I want you to get comfortable with the techniques of calculus. Okay. And by the way, that negative b over 2a, that only works for parabolas, but you could have max and min for other shapes too. Square roots, cube roots, trig, logs, exponential, right? Then, of course, we can't use negative b over 2a, but you can still do your first and second derivative tests. Okay, first derivative, 50 minus 2x. Second derivative, negative 2. Negative 2 is less than 0. Okay. Second derivative, negative means concave down. So wherever the derivative is 0, concave down, I'll have a maximum. Are we looking for a maximum? Yes, we are. Okay. So we will indeed have a maximum in this particular case, which is what we were trying to, that's what we're trying to accomplish here. Okay. All right, so set the first derivative equal to 0. 50 minus 2x equals 0. Simple algebra, x equals 25. Y is 50 minus x, so 50 minus 25 is also 25. So the answer is 25 meters by 25 meters, i.e. the ideal shape is a square, okay, as you might have anticipated. But we've now proven mathematically that that's the case. Okay. So if you have a given perimeter, okay, how should I shape it in the form of a rectangle? It must be a rectangle. Okay, what rectangle should I pick to maximize the area? The answer is to make it look like a square. Okay, so that kind of follows our intuition. You should make it into a square. Okay. All right, that's that one. I will set you up for another one. Let's see, what time is it? Yeah, I'm not sure I have enough time to do all of it, but so I'll just stop after a while and say etc. Okay, problem 14. A box with a square base and open top must have a volume of 32,000 centimeters cubed. Okay, that's logical. A volume, that's measure of how much 3D space I have, right? Maybe you need a certain number of volume to put in your stuff, right? Put in my gadgets and so forth. I need this much. Find the dimensions of the box that minimize the amount of material used. Okay, so minimum material, that would probably mean minimum cost, right? So the setup is like this. Okay, so let me lose the book in a moment. Get myself organized here. All right, so it says we have a box, square base, x by x, but we don't know this is also x, so I pick a different letter, y. And it says an open top. So can you imagine such a thing? There are 5 faces, right? Front and back, left and right, and a bottom, but no top, it says. Volume is 32,000 centimeters cubed. So what's the volume of a box? Well, it's length times width times height. So x times y, x squared y. Okay. Minimize the amount of the surface area. Okay. So I'm trying to find the surface area of the 5 faces. Well, let's see. the front, the back, the left, and the right are all the same. They're all x by y, correct? Take a look at this front. It's x by y. The back is x by y. The left and right are also x by y. Okay? So I have 4 of them. So 4xy. How about the bottom? The bottom is x squared. So I'm trying to minimize this quantity. So bottom, that says bottom there, B-O-T-T-O-M. Maybe you can't see it that well. Sorry about that. Bottom, x squared plus 4 sides, 4xy. Okay, just a quick timeout. Suppose it said instead of an open top, it was a closed box. It was completely closed. Can you see I just make one small change to this? How would that be affected if it said there's a closed box? Now there would be 6 faces. There's a top. What's the area of the top? Also x squared. So if the problem had said there was a closed box, I put a 2 there, 2x squared, and this would still be the same. So that would be the only change. All right, so the protocol would be this. I have 32,000 equals x squared y, solve for y, right? So the normal protocol is solve for the variable that is not x. Okay, so how do I solve for y? Simple, just divide by x squared. So y is equal to 32,000 over x squared. Okay. That gets plugged in right over here. And if you just look overall, what's going to happen? I will have an expression that only involves x. That's what you want. Right? You don't want x and y. You just want x. So x squared plus 4xy, which is all this stuff. So I now have an area function. A of x is x squared plus 4xy. Here's my y, 32,000 over x squared. Okay, and yeah, one of these x's cancels one of these x's. There's still going to be one more x in the bottom. And 4 times 32,000 is 128,000. So my area function is x squared plus 128,000 over x. And that's the quantities you want to minimize. Okay, so I'll just say et cetera, which means you try to figure the rest of that out. And restriction is that x has to be positive, right? You can't have negative distances here. No such thing. So x greater than 0. Okay, so you try to finish the rest of that problem. There's a setup. To take the derivative, I would bring that upstairs and make that x to the negative 1. If you can't see that, that says x to the negative 1 there. Okay, so do your first derivative, do your second derivative, and go from there to find the minimum amount of material needed in that situation there. Okay. All right, and I see I'm just about out of time, but yeah, I think, no, maybe I can do 15. What time is it? Yeah, I can set up 15. Similar to 14. If 1,200 centimeters squared of material is available to make a box with a square base and open top. Okay, so there's that open top again. Find the largest possible volume of the box. So this time you want to maximize the volume. Okay, so this time you have a fixed amount of material. So you go and buy material. I can only afford 1,200 centimeters squared of material. Okay, and how can I maximize the volume of the box? Okay, so I'll just give you the setup and then I'll probably stop. Okay, so same picture, x, x, y, but this time the surface area is 1,200 centimeters squared. So the surface area, just like last time, is x squared plus 4xy. Right? X squared for the bottom, there's no top, and the 4 sides is 4xy. Okay, so here's the bottom, here's the 4 sides. Okay. Now, they tell me that's equal to 1,200. So I set this expression equal to 1,200. Okay. So x squared plus 4xy equals 1,200. Solve for y. Subtract x squared, divide by 4x. So y equals 1,200 minus x squared divided by 4x. Right? Look over here. How do you isolate y? Subtract x squared, divide by 4x. Now this mess goes right there. Volume is x squared times y, but y is this. So x squared times 1,200 minus x squared divided by 4x. very conveniently, an x cancels out. Okay, and then I distribute it. So I'm going to have 300x minus 1/4 x cubed, and I'm trying to maximize this quantity this time, right? So cancel that. 4's on the bottom. 1200 over 4 is 300. 300x, and then 1/4 x cubed, and you want to maximize that volume. Okay, so I'll show you that tomorrow since I'm just about out of time. Let me check the chat quickly. Chat. Do we use optimization problems in machine learning? It depends. There's a lot of optimization if you're talking about in computer science. And computer science has a lot of applications where you want to maximize and minimize something, use the power of the computer, so to speak. So yeah, that's definitely the case. No question about it. Okay, and I think that's it from the chat. And we're just about out of time. Okay, folks, so tomorrow I'll do some more of these optimization problems, but if I have time, I might want to go back and do some more curve sketching problems also. Okay. All right, that'll do it for today, folks. So have a good day, and we'll see everybody tomorrow. Okay, bye, everybody.